In the past few months, the development of robotics has been like a storm brewing, with rapid and continuous innovation, and a variety of robots emerging one after another, each with its own unique capabilities. If we want robots to be able to flexibly and autonomously complete various tasks, from tightening screws on an industrial assembly line to cleaning, folding clothes, and cooking in a household setting, it is essential to equip them with a brain that has a high IQ. To put it in professional terms, this brain is also known as a motion planning model. Motion planning models are cutting-edge research topics, with various projects and trials, and bugs are rampant in the code. To quickly empower commercial robots with a commercial-grade motion planning model, we need to do a few things. 1. Enhance the model with more functionalities and learn new ones quickly through methods such as imitation. 2. Improve the model stability and generalization ability, make the model more modular, so that when faults occur, they can be repaired quickly and avoid affecting the entire system. 3. Make the model more standardized to support secondary development and increase the speed of the model's evolution and iteration. The good news is that LeRobot and Dora RS on Hugging Face are committed to achieving the above goals. The not-so-good news is that because LeRobot and Dora RS are being updated and upgraded daily, transplanting them onto the robot body is not so easy at the moment. We started 2 weeks ago to try transplanting the LeRobot robot brain onto the Stanford Aloha robot body. We originally thought this task should not be difficult. In the hands-on process, we found that the principle is indeed not difficult, but many details need to be done right at the same time. As a result, it took nearly 2 weeks to transplant the LeRobot robot brain onto the Stanford Aloha robot simulation body. Performing a brain transplant surgery on a robot requires 2 preparatory steps before the operation. 1. Learn the creation, usage, and data formats of the LeRobot brain. This step is unrelated to the native system of Stanford Aloha. 2. Learn the creation, usage, and data formats of the Stanford Aloha brain. This step is unrelated to the LeRobot brain. Our brain transplant surgery plan is divided into 4 steps. 1. Create the LeRobot brain. 2. Create the native environment, ENV, for Stanford Aloha. 3. Convert the output of the LeRobot brain into the input for the native Stanford Aloha environment. 4. Convert the output of the native Stanford Aloha environment into the input for the LeRobot brain. Using the Stanford Aloha native system as the framework, we replace the native Aloha brain with the LeRobot brain. To clarify all the details, it seems there is no shortcut. We read the source code of LeRobot and Stanford Aloha carefully and repeatedly. We publish our head transplant surgery process, in addition to source code reading notes both in Chinese-English. Hopefully it will be useful and helpful for the engineers in the robotics industry and researchers in academia.